Hello everyone, I am Jasmine and I work as a research scientist in the parallel computing labs at Intel. I am going to talk about some new parallel pull-push Louvain algorithms that prune unnecessary edge and vertex exploration during the community detection process of a network, and as a result are an order of magnitude faster than the prior state of the Earth. So let's begin. I'll start by answering some questions. The first question is, what is community? These are sets of vertices that have dense interconnections but sparse interconnections, making them strongly interacting entities in a network. These usually uncover hidden structures inside a graph and are strongly correlated to the functional and structural properties of the graph. The next question is, what is community detection? These are algorithms to identify communities in a network. These algorithms are used in analyzing different types of network from, for example, social network, e-commerce network, protein-protein interaction network, and networks from many other scientific domains to retrieve hidden patterns from them. Next question, how to measure the quality of the detected communities? Modularity is one such metric that measures the interconnectedness of the communities that can be computed by the equation shown on the slide. Here, C in is the sum of internal edges and C dot is the sum of internal and external edges for the community C. And M is the total edge weight of the graph. Modularity is a number between 0 and 1, and the higher the value, the better it is. In general, a community detection algorithm tries to identify communities in a way that maximizes modularity. Our next question is how to maximize modularity. As the equation says, large values of Q correlate with high Cin. And to get high Cin, the highest possible number of edges should fall in each community. Similarly, large values of Q also correlate with low C dot, and to get low C dot, we need to divide the network into several communities with small total degrees. Finding communities with optimal modularity is not that simple. In fact, it's an NP-hard problem, and therefore several heuristic algorithms are used to get good enough solutions. One such algorithm is the Louvain algorithm that maximizes modularity by following a greedy strategy. At a high level, the Louvain algorithm has an outer loop that traverses the graph in several passes to incrementally build communities. The outer loop can be divided into two phases. Phase 1 is an iterative modularity optimization phase, and phase 2 is the community aggregation and graph reconstruction phase. Phase 1 takes asymptotically more time than phase 2, and that's why we focus on phase 1 only. Before we look into the pseudocode of the Louvain algorithm, let's look into a key data structure that influences the naming of pull and push. The NCW hash map data structure is an important data structure where key is the neighboring community and value is the sum of edge weights to that community, and it represents how a vertex is connected to its neighboring communities. For example, for the graph shown on the slide, vertex 1 is neighbor to vertex 2 and 3, which are members of community 1, and hence the sum of edge weights to community 1 is 2, which means we will have an entry 1, 2 in the NCW data structure. Similarly, vertex 1 is also a neighbor of vertex 7, which is a member of community 7. Hence, the sum of edge weight to community 7 is 1, and we will have an entry 7, 1 in the NCW data structure as well for vertex 1. Now let's look into the pseudocode of the algorithm. The outer loop repeats if there is a change in the vertex community. Each vertex is initialized in its own community and the initial modularity is computed. Phase 1's inner loop starts and it repeats itself if modularity increases by a threshold at the end. For each vertex, it first builds the NCW hash map by pulling the latest community information from the neighbors. After that, it finds the best community to move into by iterating through the unique communities in the NCW hash map. Then it moves to the best community and updates the relevant community information. Once done for all vertices, it computes the new modularity value and repeats the process if modularity increased by a threshold. When modularity stabilizes, it exits phase 1 and enters to the cluster aggregation and graph reconstruction phase, where it creates a new graph by merging all vertices in the same community into one and connecting them by the aggregated edges as shown in the figure. We call this standard Louvain algorithm a pool-based Louvain algorithm because to build the hash map during each iteration of the inner loop, it creates the NCW data structure by pulling the latest information from the neighbors. Now let's look into what are the sources of unnecessary work here. While analyzing the Louvain algorithm, we made the following observations. We observed that for a given outer loop, the number of vertices that change their communities drops significantly after the first few inner loop iterations, as shown by these two graphs for John Hopkins and Pockett. The number of vertices that change communities in the latter inner loop iterations is also minimal, as is evident by this flattened curve. Therefore, it seems wasteful to scan all neighbors and to compute the NCW hash map if there is no change in the neighborhood. It also seems wasteful to iterate over all vertices for each inner loop iteration if vertices do not move. So the next question is, how do we prune these unnecessary vertex and edges? Before answering that question, let's look into another type of Louvain algorithm that we call push-based Louvain algorithm. And in this paper, we also proposed one new such algorithm. The main idea is that vertex does not pull, rather neighbors actively push changes in case of a move. A push-based Louvain algorithm starts with an initialized hash map, assuming each vertex is in its own community. During phase 1, it never recreates NCW. Rather, whenever a vertex changes its community, it updates its own hash map and pushes updates to the neighbor's hash map, and that's why we call it push-based algorithm. Now let's look into some pros and cons of the pull and push algorithms. A pull algorithm does redundant memory reads by scanning all vertices and their neighbors to rebuild the NCW data structure in each inner loop iteration, even when a vertex neighborhood has not changed. So in this portion of the iteration space, a pull algorithm does redundant work. On the other hand, a push-based algorithm scans through all neighbors only when a vertex changes its community. Hence, in this portion of the loop iteration space, it would avoid unnecessary edge exploration. Together, it means that a push-based algorithm is likely to do fewer edge exploration than a pull-based algorithm in the latter inner loop iterations and will likely to be faster. However, when there is a lot of vertex moves, that is in the first few inner loop iteration, a push-based algorithm will do more memory writes to update the hash maps than a pull-based algorithm, and as a result, using push-based algorithm in these first few inner loop iterations might not be beneficial. So the take-home message here is that neither the pull nor the push performs the best across all iteration space, and therefore to get best of the both worlds, we propose a hybrid pull-push Louvain algorithm. that for a given outer loop iteration starts with a pull-based algorithm and then switches to a push-based up after a given number of iterations. This hybrid algorithm explores a vertex neighborhood only when there is a change, and by doing so, it automatically prunes a significant number of edge explorations. For example, for the Pocket and Hollywood graphs, we found that the hybrid algorithm does 6 to 13x less edge exploration. So it prunes edges by 6 to 13x compared to a standard pool Louvain algorithm. Now let's talk about vertex pruning. We already know that it is unnecessary to iterate over all vertices, and in this paper we show analytical and intuitive derivation of those vertices that can be pruned with minimal sacrifice in modularity. If we look at the modularity gain equation of moving a vertex U to a community C, we see that W, U to C, and C dot are the variable terms and others are constant. W U to C is the sum of edges from vertex U to community C, and C dot is the sum of internal and external edges of community C. If we assume that Cm is C dot over M, then Cm is a value that is less than 1, hence because M is the total edge weight of the graph. If Cw is equal to Cm times Wu, where Wu is the total edges of vertex U, then modularity gain equation can be rewritten as follows if we ignore 1 over Cm term, which is common for both both terms in this equation. We analyzed the influence of these terms in the modularity gain as the number of inner loop iteration changes, as shown in this figure. The graph shows that Cm does not play an important role in the modularity gain as we expected. On the other hand, Cw does have some influence, but after the first few inner loop iterations, that influence also dies. Therefore, it should be clear that we need to focus on the vertices whose W, U to C term decreases because of a move, and we may skip those vertices whose C term changes for a move. The impact of vertex pruning on modularity is small, especially if applied on the push phases, that is the latter inner loop iterations. So what to recompute? If a vertex moves, recomputing its first level neighbors that are not in the new community should skipping them should be good enough. Recomputing them should be good enough, and we can skip all other neighbors of that vertex. So for example, in this figure, if vertex 5 moves from community C1 to C2, we need to recompute the red vertices and we can skip other vertices. When we apply this vertex pruning technique on top of the standard pool and hybrid algorithm, we see a 4 to 12x reduction in the number of vertices. For the hybrid algorithm, we applied pruning only in the push phases. One interesting point to note that the vertex pruning does not prune any additional edges compared to the hybrid algorithm, since the hybrid algorithm was already skipping those edges implicitly. Here we show performance benefits of vertex and edge pruning on the runtime of the sequential algorithm. Edge pruning gives 1.3 to 3.9x speedup, vertex pruning gives 1.5 to 4x speedup, and vertex pruning on top of edge pruning gives up to 1.9x speedup. So the take-home message here is that even without any parallelization, edge and vertex pruning gives up to 4x speedup over the standard Louvain algorithm. Now let's look into how the parallel version of these algorithms work. In the parallel pool algorithm, each thread has its own private hash map of size max degree of the graph. For each vertex in parallel, it computes the best communities to move into and then changes the community membership atomically. And we also compute the modularity using parallel reduction. In the push-based algorithm, we use a shared global hash map of size order E that we initialize in parallel considering each vertex in its own community. In phase 1, for each vertex in parallel, it decides where to move, and if there is a change in the community, it updates its own and neighbor's hash map using locks. Now let's look into some experimental results. We have used several real-world graphs to test our algorithms, including graphs with billions of edges. We used two Intel platforms, 56 cores 2-socket Skylake machine and 72 core 4-socket Haswell machine with 1 terabyte of memory to run these programs. We show the performance of the first outer loop iteration for 4 different implementations: pool, hybrid, pool prune, and hybrid prune, and the latter two use explicit vertex pruning optimization. For the POCIC social network graph on 56 cores of Skylake machine, the pool algorithm gets 19.8x speed up, pool prune gets 78x speed up, the hybrid gets 35x speed up, and hybrid prune gets 63x speed up compared to the sequential pool algorithm. On the Hollywood graph, prune gets 12x speed up, pool prune gets 26x speed up, hybrid gets 21x speed up, and hybrid prune gets 23x speed up on 56 cores compared to the sequential pool algorithm. Now let's look into some comparison with the prior state-of-the-art Louvain algorithm from the Grappolo software package. Compared to Grappolo, our pool prune algorithm is 5 to 11x faster, and the hybrid prune algorithm is 5 to 8x faster, and it also provides better modularity value across the board. On several other real-world graphs, both pool prune and hybrid prune algorithms are 2 to 8x faster than Grappolo, and as before, the hybrid prune algorithm gives the best modularity. On relatively small real-world graphs, the Amazon and California road network, a hybrid prune algorithm is 4 to 16x faster, and the modularity value is always the same or higher compared to Grappolo. We also verified the quality of the solution based on another metric called normalized mutual information, or NMI, and here too our algorithms appear to perform better than Grappolo. Now let's look into a large real-world graph, the Fenster graph containing 3 billions of bidirectional edges. Our pool prune and hybrid prune algorithms are 2 to 4x faster than Grappolo while using the same number of cores and have better modularity values. If we compare this with a recently published distributed memory performance data in the light of how they compare against Grappolo, on the Fenster graph, we see that on 4,000 processors of Haswell machine, the distributed memory algorithm is 7x faster than the Grappolo algorithm running on 64 cores. This distributed memory algorithm applies different heuristics. For example, it also does vertex pruning using probabilities and early termination and modularity threshold cycling and so on, which was not present on the Grappolo algorithm. One interesting point to note that the distributed memory algorithm is 2.3x slower than Grappolo if both run on 64 threads. So a quick math says that since we are 2 to 4x faster than Grappolo, we expect that we will be roughly 4 to 8x faster than this algorithm as well if we run on the same platform on same number of cores. So to conclude, we show that the standard community detection algorithm does a lot of unnecessary work that can be pruned smartly. And then we show that the edges can be pruned up to 6 to 13x without sacrificing modularity, and that gives up to 4x speed up. The vertices can be pruned 4 to 12x with minimal sacrifice in solution quality, and that will also lead to up to 4x speed up. And our parallel algorithms run 2 to 16x faster than the prior state-of-the-art algorithm without sacrificing the quality of the solution compared to that algorithm. And therefore, this is really a new state-of-the-art for Louvain algorithm. We'll be happy to share the code with anyone who will be interested. Please feel free to contact me for the code. Thank you so much for your attention.